start the morning session. The first speaker is Professor Debarre coming from Jussieu. Please start.
Thank you very much. So my title is not very revealing, so I'm still writing it on. I need to go there. Okay. It's for the camera, I was told to. Okay, so the title is on a conjecture. And so the conjecture is of geometrical nature, meaning that it has to do with the field of complex numbers, but its applications, and I don't want any questions about that, are supposedly about developing a theory of automorphic forms in over local fields, like over QP and its various extensions. So I will not talk about that. The conjecture itself was made by Kazhdan at the 2022 ICM. And as I said, it has to do with a very simple objects. And so the conjecture is the following. So everything will be over C from now on. So okay, so it has to do with vector bundles over curves. So let's see be a smooth curve, smooth projective curve. Of genus G. And let E be a rank 2 stable vector bundle, rank 2 stable vector bundle over C of degree 2G minus 1. Okay, and then Kazhdan and Polishchuk define the following set, but which we will, for which we'll define a scheme structure later on. So it's a set of pairs LS, where L is an element of peak knot of C, and S is a section, actually, yeah. Okay, so far so good. And so the conjecture is the following, that has three parts. Then Fe is irreducible. B, Fe has dimension G. And the last part is that Fe has rational singularities. Yes, it's birational. The fibers are projective spaces. Okay, and so my result is the following. Unfortunately, I do not prove the full conjecture. Half of it, or 2/3 of it. So CE as above. Then Fe is irreducible. Of dimension G, so this is A and B. And there's a little complement to that, so I do not prove that it has rational singularities, but I prove that irreducible energy, normal and local complete intersection. Okay, and so I could also, so I worked over this question that Daniel Oibers mentioned to us earlier this year, and so I can also prove the conjecture in dimension 2. And then I sent my note to Braverman, who had actually written the notes of Kazhdan's talk, and he told me that there was an e-print on the archive by Kazhdan and Polishchuk, published over the summer. So part of their paper is about this automorphic forms in over local fields, but the other part is about this conjecture. So they also prove the case G equals 2, and also most of the cases when G is equal to 3, okay? But they do not prove this, so it's a sort of a nice complement. Okay, I'll talk about that later. Yes, I can say yes, yes. It is smooth, actually. So, okay, so let's, so this was sort of a presentation of the conjecture. And then let's talk a little bit about the scheme FE. Okay, so as Claire mentioned, the first thing that you want to look at is the first projection from FE to the Jacobian, which was my notation. So maybe JOC will be easier to write than P naught. Okay, so the fibers are projective spaces, and this is easily seen to be surjective, simply because the H naught of E tensor L is greater than or equal to the Euler characteristic, and Riemann-Roch tells you that this is 1. Okay, and the fibers over okay, so I need to define, I want to define some subsets, so maybe, I'm doing it in the wrong order, but so these are going to be another Lefschetz loci. So the fibers over this locus that I'm about to define is PR. Okay, so this BR here is the set of elements in the Jacobian such that the H naught is at least R plus 1. Wait. Please wait. It is actually a result of Renault from 82. Yeah, it's an result. Okay, so this is clear. So in particular, this FE is connected. So let me just go through very quickly, because this is really standard. The scheme structure of FE. So it's FE is some sort of degeneracy locus, and so it goes like this. So the scheme, and I haven't defined the scheme structure, but as everywhere, dimension at least G, and is LCI where the dimension is exactly G. Okay, so quickly, this is, as I said, very standard. So you choose D, a divisor, effective divisor on C of large degree. So that for any L in the Jacobian, H naught of E, maybe I'm not supposed to speak too loudly here. Okay, so these spaces will have a constant rank when L varies over the Jacobian. So let's say that this is dimension m plus 1, which you can compute. M is, I think, 2 degree of D, but it's not very important. And so you restrict to D, and this has dimension M. So as I said, these vector spaces have constant dimension when L varies over the Jacobian. So they are the fibers of vector bundles, F of rank m plus 1, and G of rank m. And H naught of E tensor L is the kernel of this map of vector bundles at the point L. Okay, so let's say this is alpha. And more precisely, in this fashion, you see that Fe can be considered as a subscheme of P of F. Which is just defined by the kernel of alpha. And so what else do I want to say? And so locally, meaning over a subset of the Jacobian where F and E are trivial, the map PR1, the projection, is the pullback so via a map from an open set of J of C to harm of. So this is trivial. This is now okay. And here you have, so this is sort of the universal situation. So here X is okay, so U is in here, and X is in okay. Okay, so this is easily seen to be smooth of codimension M in this product here. So in particular, when you pull back this universal situation biomorphism from an open subset of J of C to this guy here, you find that F of E is everywhere of codimension, at least, at most M, in P of F. And this gives exactly the fact that he has dimension at least G. And so since this is a pullback of something smooth, it is LCI when the dimension is exactly M, codimension M. Okay, so as I said, this is really a standard thing. And okay, so maybe I'll leave the conjecture on the board. Yes, yes. Yeah, I'm going to mention that also. Yeah. So now if you think about it, so you have this map here, and so as Claire mentioned, this is an isomorphism, or maybe when I mentioned here, PR of 1, PR1, sorry, is an isomorphism over the complement I mean, it's an isomorphism over the set of L such that this is equal to 1. Okay, so it's an isomorphism over the complement of B1. B1 being defined over there. Okay, and so this gives you over this open set, this gives you a component of dimension G because it's birational to the Jacobian. Okay, even an isomorphism. So if you think about it for a second, you'll see that the part A and B of the conjecture are equivalent So obviously you want B1 of E to be of codimension at least 1. You want it to be a proper subset. Otherwise it will give you a component of too large a dimension. But you also, if you want Fe to be reducible, you want this guy to have that codimension at least 2, okay? And the same for the others. So equivalent to, for any R, at least 1 codimension of Br of E is greater than or equal to R plus 1. Okay, so this is the codimension in the Jacobian. Okay, so let me call that star R. Okay, so this is sort of the elementary remark. So if you look in the literature, you find that people have worked on this kind of question quite a lot. So I think the oldest result is a result of Renault from 82. So in 82, so actually it didn't really not completely what we need, but it's a result in the right direction. He proved that B1 of E is maybe I'll write it in the same way. The codimension is at least 1. So in other words, he proved that, I mean, his result is a more general result, but in our case it says that when L is generic, H naught of E tensor L is 1, exactly 1. Prove that the codimension okay, so not quite enough for star 1. So as I said, his result is more general. I think Renault's result is that for any stable rank 2 vector bundle, maybe semi-stable rank 2 vector bundle on a curve, H naught of E tensor L is equal to, when L is general in the Jacobian, is equal to the maximum of the Euler characteristic and 0. Okay? Any degree. Rank 3, okay, it certainly gives counterexamples in higher ranks, but higher means either 3 or 4. Rank 4, yeah.
And I think it's called radial.
So his proof is actually very nice. Okay, so this is not quite enough for us. So you look further in the literature and you find that in 17 years later, Brivio and Vera actually proved star 1. So meaning that the codimension is at least 2. So this is nice. There is also a result from 2001. So this guy showed, I won't pronounce the first name, I don't know, and Sols. They proved the last one, meaning that so star G means that the codimension is at least G plus 1. So in other words, BG of E is empty. So in other words, it means that H naught of E tensor L actually for any E stable is at most G. Okay, so as far as I could tell, this was the sort of state of the art. So it turns out that proving all these inequalities is not very difficult. So this kind of inequality is sort of a Clifford type result for vector bundles. So there's also a lot of work on those. Okay, so the first lemma is the following. And this lemma will show that it's enough to prove star 1, which is already known, and star 2. So the lemma says that, let's say for R at least 3, there's an inclusion and in particular, this implies that the dimension of BR of E is at most the dimension of BR minus 2 of E minus 2. Okay, so this is an inclusion, remember, this is in the Jacobian of C, and so C minus C is what you think is the set of, so the curve C embeds into its Jacobian, and so you can see C as a subset in here, not really well defined, but the set of differences is well defined. Okay. So the proof is totally elementary. So if you want to prove this, you take an element in here, so L in BR of E, so this means that the space of sections of E tensor L is at least, has dimension at least R plus 1, and you want to prove that if you replace L with L of P minus Q, then this is greater than or equal to R minus 1, but this is obvious because so P and Q are 2 points of C, so this is greater than or equal to E tensor L minus Q. And since this vector bundle has rank 2, this is greater than or equal to H naught of E tensor L minus 2. And so this is what we need, okay? So this proves this inclusion here. And for the next one, this is actually a general result, which says that, so for the second part, use the fact that whenever you have a sobriety, let's say Z of of J of C. So this is true in any abelian variety. It doesn't have to be the Jacobian of the curve, but whenever you have a, okay, so whenever you have a curve, but for us it's going to be C, but that generates, then the dimension of Z plus C, generating curve, of Z plus C is the dimension of Z plus 1. Except, of course, if Z is the whole thing already. Okay? So, using this remark then, you can deduce the second part. And the thing is that since R is at least 3, this guy cannot be the whole thing by Reynolds result. Okay? So you're not in the exceptional case. So that's the end of the proof. So you see that if you want to prove these inequalities, then it's enough, as I said earlier, it's enough to prove star 1, which is already known, luckily, and star 2. This is not easy to prove. I mean, this is, takes up several pages, of, which I checked. Okay. So what about star 2? Well, then you need to prove star 2. So the idea of the proof is similar to what I did here, except it's a little bit more complicated. So this is the second lemma. So it says that the codimension of BR of B2 is at least 3. Okay, so let me go through the proof. So assume to the contrary that there is a subvariety of B2 of codimension 2. Okay, and we want to obtain a contradiction. Okay, so I will use the same kind of construction. So I will consider so which one is it? The difference map. So again, the curve C is not really contained in the Jacobian, but up to translation it is, and so it doesn't make any difference. So let's pretend that it is. So this is a difference map. And because of the result that I stated there, the image is a hypersurface. So it's irreducible. So B is irreducible. So this is an irreducible hypersurface. Okay, so I'm doing the same thing as here, but except a little bit more carefully. Okay, so then I do the sum map. So this is the difference map, this is the sum. And now since D is a hypersurface and the curve C still generates a Jacobian, this will be surjective. Say of degree E. Okay, and if you think about it, this is just the intersection number of D with C, with minus C, but it's the same number. Okay, so now take a point, a general point here. And so since this map here has degree E, you can write it as x1 plus, let me keep the same notation, Okay, so the xi are points of D and the pi's are points of C, distinct, because M is general. And in turn, we can write each xi, which, since it is in the image of the difference map here, over there, xi is Li of minus Qi. Okay, so Li is in B and Qi is in C. Okay, so putting everything together, we obtain that M is Li of Pi minus Qi. Okay, and then we do the same. Now it's gone, but we do the same estimate that was here earlier. Okay, so H naught of E tensor M. So we write M. Okay, so first, let's say this is greater than or equal to E tensor M minus Pi, obviously. But M of minus Pi is equal to Li minus Qi. And so remember that Li is in B, so in particular, the H naught of E tensor Li is at least 3. So first of all, so as before, this is because E has rank 2, and as I just said, this number is at least 3, so this is at least 1. But M is general in the Jacobian, so by Redow's result, this is 1. So in particular, all these inequalities are equalities. Okay, and in particular, there's equality here, which means that the section, the unique section of E tensor M vanishes at all points Pi. Okay, so we get an inclusion. So we get, since the points Pi are distinct, we get an inclusion. And so remember that E is stable. By stability, this is the number E, or the degree of this sublime model is at most 1/2 of the degree in here. So in particular, I mean exactly, this is at most G minus 1. Okay, so what good does this does to us? Well, so there's something about the degree of curves in abelian varieties. So that says that it's a general theorem that if D is ample, then the degree of any curve is at least G. This is something that's known. So in this case, we get a contradiction. So how do we know that D is ample? Well, we don't know that it is ample, but it is ample, for example, if the Jacobian is simple, if it doesn't have, any proper abelian subvarieties. So this is okay when in general, you have to work a little bit more And so in general, if D is non-ample, it is still the pullback of an ample vector, of an ample divisor on the quotient of the Jacobian. So you have to work a little bit more, actually quite a bit more, but you can do it. But I won't do it here. So anyway, this is a full proof in case where J of C is ample, is simple, sorry, but I won't do it. Okay, so where are we now? I've proven actually all these inequalities star R, so I've proven A and B. For what?
I mean, I understand it.
For this, you absolutely need stability, otherwise.
So in all the other cases, it's wrong.
If you take either for either sum of two line bundles, then
Yeah, sure, that's it.
this okay. If you take either sum of a line bundle of degree
No, but you can. Yeah, there is this Segre invariance for bundles, or the stabilization, iteration of the space of the
Yeah.
bundles.
But yeah, in general, you really need stability. I think it's. You see, if E is a direct sum of line bundles, one of them has very high degree, then these spaces will have very high dimension for any L. So. Well, this is degree 2G minus 1, rank 2, so this is equivalent. Yeah, thank you. So, what can I say? So, what about normality? Yes.
Maybe could you mention how you prove this inequality for ample divisors that times C is at least G?
I could, yeah, but I won't. No, it's actually something. It's classical, but I don't remember. Let me try to think.
But at least who's the result?
I proved it a long time ago, but I'm sure that it was known before. I proved sort of an improved version of this. Improved in the sense that it's at least something times the degree of this guy. So okay, there's Matsuzaka's criterion, I think, that says that if you have an ample divisor and a curve, and D dot C is equal to G, then it's the Jacobian of the curve, and D is the principal polarization. So, yeah, I think Matsuzaka's criterion says exactly that there is this inequality, and if there is equality, then it's the Jacobian of a curve, and D is the canonical principal polarization. Yeah. It's not very difficult, but okay. So there were okay, yeah. So what about normality? So I've given this talk before. I don't remember if I had normality at the time, but this is actually to prove normality. I use a lemma which is in the paper. From Kazhdan Polishchuk. Yes. Sure. Yes. Okay.
pi bytes, just one. So something you need more.
I need the curve to generate the abelian variety.
This kind of thing.
Yes, yes.
Okay.
Irreducible and also irreducible, otherwise you can take 2 copies of the, yeah.
Not on the other, not on the other.
Yes, yes. I need the C, yeah, so what I said earlier was wrong. You're right, so D is ample and the curve C generates the abelian variety. Then you have this, and if there is equality, then so. Thank you. No, thank you. Yeah. So Matsuzaka. I think it's Matsuzaka. Okay, and so the lemma says the following, that there is identification between Fe, so the set of pairs, it's still on the board, and a quad scheme of quotients of E of, so E, Q, sorry, has rank 1 and degree to G minus 1. And so the isomorphism comes from by sending L and S to the quotient. So S is a section of E tensor L, which you can see as a map from L inverse to E. And you send that to the quotient and for quad schemes, there is there's a criterion for smoothness. So it's the x1 of the quotient. So let me write it this way. Suddenly, no, it's the other way around. Okay, so then you have to work a little bit more. Maybe I should say that. So since we know this that Fe is irreducible of dimension G, it is LCI. This is something I mentioned here, sort of from the general fact that I mentioned earlier. So to prove that it's normal, you only have to prove that it's smooth in codimension 1. And so using this this remark here, all you have to prove is, so you have to bound dimension of locus where this x1 is non-zero. Okay, so this you need to do. So here again, I need to use another result of Brivio and Vera. This was part of the same paper. But anyway, so this can be done, and then you can prove a normality.
What's the simplest example when thing is simple?
Okay, I'll maybe say a few words about it. So I still have 15 minutes. So what else can I say? Okay. Okay, so I want to comment on what Claire said earlier. So this is a remark that's in the Kazhdan Polishchuk paper. So let's say maybe comments. So first of all, to answer Gabi's question, it is known when E is general, so general means general in the moduli space of stable rank 2 vector bundles on C of degree 2G minus 1, then Fe is smooth. So this comes from studying sort of a global situation over the whole moduli space. So you have a moduli space of, let's say, yeah, what is the notation? UC 2, rank 2, degree 2G minus 1, stable vector bundles of degree, rank 2, the degree 2G minus 1. And so there is a, I think it's called, so okay, let me, so this is certainly smooth of dimension 3G minus 3. I think we saw that in Gabi's talk. And this guy here, SU is when you fix the determinant, right? I don't want, 4G minus, thank you. Okay, and so this is the set of, I mean, the moduli space of vector bundles, and here you choose a section. Okay, so this is ES. And this is the forgetful map. So this guy is smooth. This guy was also proven to be smooth of the same dimension, smooth irreducible. And using that, it's not very difficult to deduce by general smoothness that this guy is smooth when E is general. Okay, so at least in this case, this is it proves the conjecture. Okay, I think. Now, if I want to go back to any E, not just a general E. So it's not very difficult to see that the map, which I call PR1, is actually the blow-up of the scheme, and this is important. Okay, so now I forgot to mention at the beginning that so these BR of E are degeneracy loci. So they have an expected codimension. Yeah, you're right. The first one, the first non-trivial one. Yeah. Okay, so I should have mentioned earlier that the expected codimension of BR of E. So remember in the notation of the lemma at the beginning of the talk, this BR of E is really degeneracy loci for the map alpha from vector bundles F to G. okay? So they have an expected codimension, and this is R plus 1. So this is much larger than what we proved, which is that the codimension is at least R plus 1, okay? Except when R is equal to 1, okay? So this guy here has, it has the expected codimension 2. Okay, and so the thing is that this scheme here can be rather bad. Okay, if you look at points. Not that I know of. It's so the thing is that at a point of B1 minus B2, so in other words, where H naught of E tensor L is exactly 2, then the scheme is locally a complete intersection. It's locally given by 2 equations. And so it's very easy to see that there are 3 possibilities. Either, so let's say point L, either B1 of L is smooth at L, and then obviously the blow up is smooth because you're blowing up a smooth subscheme. So it's smooth over the entire pre-image of L. So this is a P1. Okay. Or let's say the dimension of the Zariski tangent space of B1 at L. So this was the case where the Zariski tangent space has dimension G minus 2. So if this is dimension 1, then you can check by a local calculation that Fe has a unique singular point over the pre-image. And the last case is when the dimension of the Zariski tangent space is G. So Zariski tangent space is the whole tangent space to the Jacobian. Then it's easy to check also that Fe is singular along the whole of P1. Okay, and in this case, sorry, I forgot to say that it's a unique singular point and it is rational singularity. Okay, so in this case we're fine. In this case, we don't know. So what can I say? So in particular, normality says that this cannot happen on a whole component of B1 of E, otherwise it will give you a singular locus of codimension 1. And however, there are examples of E, and really concrete examples, you can construct E really explicitly for which, for any G, B1 of E has a non-reduced component Okay. So in particular, we are in one of these two cases, and since we know by other means that the FE is normal, it means that at least it means that FE has a singular over this component. This is singular. The singular locus has a component of codimension 2. Okay, and so what can you say? That generically you cannot be in this second case because this will give you a singular locus of too large a dimension. So you know that at least generically over this component, you are in this situation here. So this gives you in any genus examples of E for which FE is singular, is actually singular in codimension 2. Okay, so what else can I say? So this was the first remark. The second remark is that, and this is, so I don't remember if I mentioned it, but Kazhdan and Polishchuk proved the conjecture, the full conjecture, including C in genus 3 for non-hyperelliptic curves. And the difficulty is that over a point of B2, so this is a point where the number of section is 3. So the locus, the scheme that you're blowing up, which is B1 is not LCI. It's Cohen-Macaulay. Do we know that? Maybe not. It's not LCI. Okay, so in this case, you're blowing up a subscheme which is not LCI, and it's, I don't think there's any general result to prove that the blow-up has rational singularities. So it can very well happen in some cases that B2 of E actually looks like the 3 coordinate axes of a 3-dimensional space. Okay? And usually you don't want to blow up this, but here you have to blow it up, and you check by just direct calculation that the blow-up has rational singularities. And this is what they do. They go through a whole list of possible subscheme like this. Okay? Because so B2 of E is empty when G is equal to 2, so this makes sorry. Okay, so in genus 2 this is empty. This can happen in genus 3. Well, you need to be in a 3-dimensional space at least. It may happen. Okay. So in other words, they examine all possible shapes that this scheme has when G is equal to 3. They prove the conjecture when G is equal to 3 and C is not hyperelliptic. This is the sort of a difficult point. I mean, the one I didn't prove, so. And, okay, so I guess I'll stop here. So, I mean, usually I asked several people, and it turns out, I mean, the answer is that it's very hard to prove that something has rational singularities if you don't have a desingularization, sort of a canonical desingularization. Anyway, thank you very much.
Any questions? Welcome.
Mm-hmm. Yes, there are many results. Yeah. But it's hard to translate them into anything useful in this case. Yeah, I looked them up. I think the first results were due to maybe Laszlo. Many people. Since then, I mean, Laszlo, that was a long time ago. Mm-hmm. Yeah, but this is a bit far away because the theta divisors are not principal polarization, so in this case, so yeah, they're in 2 theta, yeah. Mm. Mm. Yes. Yeah. Yeah. Well, this is used by Preview and Vera in their proof, of course, a lot of things like this, but yeah.
So if you have you have this expected codimension, which is much higher, R times R plus 1.
Yes.
So if E is generic and C is generic, is this true?
I don't know that, yeah. I've looked at it because I think the point of this is that you don't want E to be generic. But yeah, of course, this is a natural question. Yeah. So he's asking whether. So there are examples where, yeah, I didn't mention that, but there are examples where these inequalities, star R, are all equalities. So you can construct an E, it's more or less the same as this one, for which the codimension is R plus 1. Okay, so this is sort of the worst case. You're asking whether when E is general, you are in this nice case here.
Well, I think you have to put also C general.
Also C general.
Yeah, in the universal C.
If everything is general, then probably. You know that better than me, no? That. I mean, if C and E are general, then you just have to look at the universal situation. I mean, just have to look at it. Yeah. Yeah.
So why did they, you asked, okay, nevertheless I will ask the question. So why did they conjecture this statement about the rational singularities? Why exactly?
I don't know. I mean, I don't understand that part of the paper, so it has to do with a sort of a, no, I don't know.
What does it bind?
I don't know. I mean, they construct matrix on some weird spaces. I don't know. Sorry.
What happens if C is hyperelliptic?
What do you mean, what happens? It's bad. It's bad. I mean, for example, they proved. Well, so for example, they proved the conjecture when G is equal to 3 and C is not hyperelliptic. I mean, all these examples, I mean, this example, for example, the curve is hyperelliptic. So the more special the curve, then the worse the situation can be.
Yeah, of course.
Yeah.
If you understand the worst possible situation. One thing is that for a hyperelliptic curve, the moduli space is well understood. It has the moduli space of stable sheaves has a description in terms of intersection of quadrants. So,
Maybe, yeah.
does this question has some relation in terms of this intersection of two quadrants?
I don't know. This is good. This is a good point. Yeah.
I mean, of course, this is S here, not U.
Yeah.
But still.
Yeah. I don't know.
You have questions? Okay, start speaker again.
Thank you.